Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Controlling Electromagnetic Fields, a Critical Evaluation, the 1999 publication Controlling Electromagnetic Fields by John Pendry, David Schurig, and David Smith represents a significant contribution to the field of metamaterials and their application in manipulating electromagnetic radiation. It laid foundational groundwork for concepts that would later revolutionize cloaking technology and numerous other applications. This essay delves into a section-by-session critical evaluation of the work, assessing its claims, methodology, and overall impact on the scientific community. Section 1, Introduction of Effective Medium Theory. The initial portion of the paper introduces the concept of effective medium theory as a means of describing the electromagnetic properties of composite materials. It posits that, under certain conditions, a heterogeneous material can be treated as a homogeneous medium with effective permittivity, denoted as epsilon, and effective permeability, denoted as mu. The claim is that these effective parameters can be calculated based on the properties and arrangement of the constituent materials. The argument hinges on the wavelength of the electromagnetic radiation being significantly larger than the characteristic size of the inhomogeneities within the material. This allows the fields to see an average response rather than resolving the intricate details of the microstructure. Evaluation of this claim requires a consideration of the limitations inherent in effective medium theory. It is crucial to acknowledge that the theory breaks down when the wavelength approaches or becomes smaller than the size of the inclusions, or when strong scattering effects become significant. The paper acknowledges these limitations implicitly by focusing on structures where the homogenization approximation remains valid. The section establishes the theoretical framework upon which the subsequent development of metamaterials with unconventional electromagnetic properties is built. The assumption of homogeneity, while powerful, necessitates careful consideration of the physical dimensions and operating frequencies to ensure validity. Section 2, the split ring resonator as a metamaterial building block. This section explores the split ring resonator, often abbreviated as SRR, as a fundamental building block for constructing metamaterials with tailored electromagnetic properties. The core claim is that these resonators, well arranged periodically, can exhibit a strong magnetic response at specific resonant frequencies, leading to a negative effective permeability in a narrow frequency band. This is achieved through the excitation of circulating currents within the ring structure by the incident electromagnetic field. The split in the ring introduces a capacitance that, in conjunction with the inductance of the ring, determines the resonant frequency. The paper supports this proposition with simulations and theoretical analysis demonstrating the relationship between the SRR geometry and its resonant behavior. The methodology involves solving Maxwell's equations for the SRR structure under different excitation conditions and extracting the effective permeability from the simulated field distributions. A crucial aspect of the evaluation involves considering the losses inherent in metallic structures at high frequencies. These losses can significantly dampen the resonance and broaden the bandwidth of the negative permeability response. The paper addresses this to a degree, but later work has emphasized the importance of minimizing these losses for practical applications. The split ring resonator concept represents a clever engineering solution for achieving artificial magnetism at frequencies where naturally occurring materials do not exhibit such behavior. This opens the door for designing materials with entirely new electromagnetic properties. Section 3, Achieving Negative Permittivity with Metallic Wires. The paper then pivots to the discussion of achieving negative permittivity using thin metallic wires. It claims that a periodic array of such wires can exhibit a negative effective permittivity below a certain plasma frequency. This phenomenon arises from the free electrons within the metal responding collectively to the incident electromagnetic field. The electrons oscillate in response to the field, creating a polarization that opposes the applied field thereby leading to a negative permittivity. The argument is supported by a crude model analysis of the free electron gas in the metal. This model predicts a plasma frequency below which the permittivity becomes negative. The paper outlines the relationship between the wire geometry, the metal properties, and the resulting plasma frequency. Evaluation requires paying close attention to the assumptions underlying the Drude model. This model assumes that the electrons move freely without collisions, which is an idealization. In reality, collisions with the lattice and other electrons introduce damping and modify the frequency dependence of the permittivity. These effects are particularly important at higher frequencies. Furthermore, the paper notes limitations due to the finite size of the wires. The concept of using metallic wires to achieve negative permittivity is significant because it provides a complementary approach to the split ring resonators for tailoring the electromagnetic properties of metamaterials. The combination of negative permittivity and negative permeability, as explored in subsequent sections, leads to fascinating possibilities. Section 4 Composite metamaterials exhibiting negative refraction. This section integrates the concepts of negative permittivity and negative permeability to propose the creation of composite metamaterials exhibiting negative refraction. The central claim is that a material possessing both negative permittivity and negative permeability will exhibit a negative refractive index. This implies that electromagnetic waves propagating through such a medium will bend in the opposite direction compared to ordinary materials. The argument is rooted in the relationship between the refractive index, the permittivity, and the permeability. The refractive index is equal to the square root of the product of epsilon and mu. When both epsilon and mu are negative, the refractive index becomes negative. The paper presents numerical simulations demonstrating negative refraction in a composite structure consisting of split ring resonators and metallic wires. These simulations show that an electromagnetic wave incident on the metamaterial slab bends away from the normal in a way that is consistent with a negative refractive index. Evaluation requires scrutinizing the simulation parameters and ensuring that the structure is operating within the regime where effective medium theory is valid. It is also vital to acknowledge that negative refraction is accompanied by significant losses, particularly at the resonant frequencies of the SRRs and near the plasma frequency of the metallic wires. The practical realization of negative refraction requires careful impedance matching to minimize reflections at the interface between the metamaterial and free space. This section represents a pivotal point in the paper, as it connects the individual components of the metamaterial to a macroscopic phenomenon of negative refraction. It is this phenomenon that holds the key to many of the potential applications of metamaterials, including cloaking and superlensing. Section 5 Focusing of electromagnetic waves with a negative refractive index lens. The paper expands upon the concept of negative refraction by proposing the use of a metamaterial slab with a negative refractive index as a lens to focus electromagnetic waves. The claim is that such a negative lens can focus waves beyond the diffraction limit, potentially enabling superlensing capabilities. This arises from the fact that a negative refractive index material can restore evanescent waves, which are typically lost in conventional lenses. Evanescent waves carry information about subwavelength features of the object being imaged. The paper illustrates this concept with simulations showing a focusing of electromagnetic waves by a negative lens. The simulations demonstrate that the image formed by the negative lens is sharper and has a higher resolution than the image formed by a conventional lens. Evaluation requires careful consideration of the losses within the metamaterial and their impact on the image quality. Losses can degrade the focusing performance and limit the resolution of the lens. Furthermore, the paper notes limitations due to the finite bandwidth of the negative refractive index material. The negative lens concept is particularly exciting because it challenges the conventional wisdom of diffraction-limited imaging. It offers the potential to create microscopes with unprecedented resolution enabling the visualization of structures at the nanoscale. The practical implementation of negative lenses requires overcoming significant technological challenges, including minimizing losses, achieving precise control over the metamaterial structure, and impedance matching to the surrounding medium. Section 6 Controlling wave propagation and potential cloaking applications. This section anticipates the applications of metamaterial control of electromagnetic waves, specifically hinting at cloaking potential. The paper proposes that by carefully engineering the permittivity and permeability of a metamaterial, it is possible to manipulate electromagnetic waves in a way that avoids scattering and renders objects invisible. The claim is that a cloak made of such a metamaterial can guide electromagnetic waves around an object, effectively hiding it from detection. The logic is that if the permittivity and permeability are precisely tailored, waves will propagate around the object without any reflections or distortions. This phenomenon is reminiscent of how water flows around a smooth rock in a stream. The paper does not present a detailed design for a cloaking device, but rather outlines the theoretical framework for achieving cloaking based on controlled electromagnetic properties. Evaluation involves a recognition of the extreme challenges associated with designing and fabricating such a cloak. Achieving the required precision in the metamaterial structure is a formidable task. Furthermore, a cloak must be designed to operate over a broad range of frequencies and angles of incidence. This section marked a significant turning point, as it presented the possibility of manipulating electromagnetic waves in a way that was previously considered to be impossible. While the paper stopped short of demonstrating a working cloak, it lays the groundwork for future research and development in this area. The idea of cloaking captured the imagination of the scientific community and the general public, leading to intense interest and investment in metamaterials research. Section 7 Limitations of effective medium theory in metamaterial design. This portion, less explicitly stated and more implicitly woven throughout, touches on the limitations inherent in applying effective medium theory to metamaterial design. The paper subtly acknowledges that as constituent element size approaches wavelength, the effective medium approximation falters. This is critical to assessing the broader claims. The argument centers on the fundamental assumption of homogeneity breaking down when the wavelength becomes comparable to the microstructure scale. The paper addresses it through careful selection of simulation parameters and by acknowledging the frequency dependence of the effective properties. A rigorous evaluation necessitates recognizing that while effective medium theory provides a useful first-order approximation, more sophisticated techniques are needed for accurate modeling and design, especially at higher frequencies or with complex unit cell geometries. Finite element analysis and other full-wave simulation methods become essential for capturing the intricate electromagnetic interactions within the metamaterial. It underscores the continuous need for refinement in theoretical tools to keep pace with the growing complexity of metamaterial structures. It also serves as a reminder that the design process often involves a combination of theoretical modeling, numerical simulation, and experimental validation. Section 8 Technological Challenges and Future Directions. The concluding portion highlights the technological hurdles and outlined promising avenues for future exploration. Fabrication and material losses represent the most significant challenges. The paper posits that overcoming these limitations requires further advances in nanofabrication techniques and the development of novel low-loss materials. The argument is that precise control over the geometry and composition of the metamaterial building blocks is essential for achieving the desired electromagnetic properties. The paper also envisions the exploration of new metamaterial designs, including three-dimensional structures and materials with tunable properties. An evaluation would necessitate an appreciation for the multidisciplinary nature of metamaterials research. It requires expertise in electromagnetics, materials science, nanofabrication, and computational modeling. The paper's call for technological innovation and the exploration of new concepts reflects the dynamic nature of the field and the potential for future breakthroughs. It inspires the development of more sophisticated fabrication methods like focused ion beam milling, electron beam lithography, and self-assembly techniques. It also motivates the search for novel materials with lower losses and higher operating frequencies. In conclusion, controlling electromagnetic fields represents a cornerstone in the modern development of metamaterials. Its claims regarding the possibility of engineering materials with tailored electromagnetic properties, including negative permittivity, negative permeability, and negative refraction, have been substantiated by subsequent research and experimental demonstrations. While the paper acknowledges the limitations of effective medium theory and the technological challenges associated with fabrication and losses, it provides a clear and compelling vision for the future of metamaterials research. The work's sustained impact stems from its clear articulation of the fundamental principles underlying metamaterial design, its presentation of novel concepts such as negative refraction and cloaking, and its stimulation of widespread interest and investment in this fascinating field. The paper's legacy resides not only in its specific findings but also in its encouragement of a paradigm shift in how scientists and engineers approach the manipulation of electromagnetic waves. Its careful balance of theoretical rigor and practical considerations ensured its reception as both a scientific inspiration and a technological roadmap.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.